All right, in this video, we're going to be starting Chapter 2, Unit 2, which is going to be on linear equations. Today, we're going to be focusing on this concept called the rate of change. And the rate of change has to do with the comparison between the dependent and the independent variables. So, the definition of the rate of change is the change in the dependent variable divided by the change in the independent variable. And what a rate of change allows you to do is allows you to see the relationship between two quantities as they change. All right, so to put some context to this, let's take a look at this first example here. Finding rate of change using a table. So off to the side, you see that there is a table that shows the cost of renting a table saw. Um, for one day, it's going to cost $60. For 2 days, it's 75. Three, it's 90, etc. So we have an independent variable. So the first thing I'd like you to do is get used to really paying attention to what the units are. So the unit for the independent variable, that would be the number of days. The days or the cost depends upon the number of days. So the independent variable is days, and the dependent variable is the dollars. That would be dollars. More specifically, it would be the cost for renting the saw. Okay. What does the rate of change represent? So, once again, if we think about what the rate of change represents, it's a look at how the dependent variable is changing compared to the independent variable. So, if we think about the unit that goes with the rate of change, the dependent variable is on top and the independent is on the bottom. So when we're talking about the rate of change, we're talking about the number of dollars per day. Unit on top, the dependent is dollars, the independent is days, so we get a unit of dollars per day. Okay, what is the rate of change between each consecutive day? And so if I look at this, I see that the rate of change, so the change in the, if I look at just day one to day two, then I see that I go up $15 and this goes up one day. If I look at this, the next consecutive, that goes up $15 and the independent goes up by one day. And that continues 15, 15, and this goes up by one and goes up by one. And so when we have a consistent rate of change, the rate of change is always $15, then what we have is something that will end up being a linear equation, but we'll get to that soon enough. So what is the rate of change between each consecutive days? We would say $15 is the dependent change. One day is the independent change. And so I probably would call that $15 per day. All right. Then, just to kind of check, what is the rate of change between any 2 days? So we did consecutive days, but let's just pick, for no particular reason, let's just pick, I don't know, day 2 and day 5. So what's the change between day 2 and day 5? Well, to find the change in something, we would subtract them. So 120 minus 75 is going to be, looks like 45. And the change in the independent variable is going to be 5 minus 2, or 3 days. And so we would have $45 over 3 days. But we can reduce 45 thirds, and that ends up being $15 for one day. And we get the same rate of change that we did when we looked at every consecutive one. So when we're dealing with something called a linear equation, that will always happen. The rate of change is consistent the whole time. So whether or not you look at it day per day, or you look at the total, or any set of data, it should come out to be a rate of change that stays consistent. All right, let's graph this data on the XY axis. And looks like all of my data is positive. So I'm just going to go ahead and I'm going to treat this as just the first quadrant. So there's my X and there's my Y. My X is in days and my Y is in dollars. All right, and so now I need to graph this. My first thing I need to do is kind of come up with a decent scale. 60 to 120. Let's see how much I got to work with here. 10, 20, 30, 40, 50, 60, 70, 80, 100. I could go by tens pretty easily. I think that's probably what we'll do. So we'll count these by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 10, 20, 30, 40. And we'll do these by ones. All right, let's now graph our data. One day, $60. So independent is 1, 60. So we're going by 10, so it'd be $60. 2 days, $75, so halfway up. 3 days is 90. 4 days is going to be 105, halfway up. And day 5 is 120, which would be right there. All right, so we see that we have, if we connected these with a line, then we could project up and kind of see where this is heading, and come up with, we could use this to figure out if I was going to keep it for 10 days or whatever. All right. So that is our graph. You can see it did make a line, right? They are all in a straight line. I went up 15 and over 1 day, up 15 over 1 day. So it stayed consistent the whole time. And even if we say we went all the way from maybe from here all the way over to here, it's still going to reduce to 15. 10, 20, 30, 40, 50, that's a change of 60 over a change of 1, 2, 3, 4. 60 over 4 is 15. So however you look at this, we went up 15 and over 1 as an average rate of change. Okay, let's keep going. All right, you can use a graph to find the rate of change. Recall that the independent variable is plotted on the horizontal and the dependent's plotted on the vertical. And then that makes the rate of change, you could think of it not just as the change in the dependent over the independent. Since the dependent is the vertical, you can look at it as vertical or horizontal change, which is what we just did when we looked at this graph, right? Notice I was looking at how much vertical change compared to the horizontal change. All right, so let's take a look at example 2. Finding rate of change using a graph. Airplane altitude. The graph shows the altitude of an airplane as it comes in for a landing. What is the unit of the independent variable? So my independent variable is always going to be the horizontal one, so that's going to be seconds. So it's time, but specifically the unit is seconds. And then the dependent variable is the altitude, but specifically it is altitude. It is in feet. So that means when we look at the change in our dependent, that's going to be change in feet over change in seconds. So the unit for this is going to be in feet per second. All right. So what we need to do is kind of find some data points that we can use to do some counting. And it's given us a couple to look at. So it's given us this point right here, which is 60, 100, 1,000. and then it's given us 180 and 0. So the vertical change, that would be the change from here to here, is going to be what? 1,000 minus 0. We're at a height of 1,000, and then we're at a height of 0. So that's 1,000. And then my horizontal change, we went from 60 to 180, and that would be 120 total seconds. All right. Now, what we didn't talk about is direction yet. So let's think about this for a minute. Time is increasing with as our independent variable. So as time is getting larger, so we're moving to the right, my altitude is getting smaller. And so I have gone over 120 seconds of time, and my feet has dropped by 1,000. So I'm going to go ahead and label this as negative 1,000 because we went down 1,000. So then what's my rate of change? It's simply going to be negative 1,000 over 120 seconds. I lost 1,000 feet over 120 seconds. This reduces, we can cross off one of the zeros. And so we're down to negative 1,000 over 12. I'm sorry, negative 100 over 12. And I know that 4 goes into both of those, so I'm going to reduce it. This becomes a negative 4 times a 25 over 12 is 4 times 3, so my 4's cancel. So I get negative 25 thirds. Again, feet, and we could change it to kind of write it out as words, feet per second. And if we wanted to change that into a nice mixed number instead, so we can get a little bit better understanding, it would be, we're going down, let's see, 8 times 3 is 24 with a remainder of 1. So we're doing 8 1/3 feet per second. So my rate of change, I'm going down 8 feet, 8 1/3 feet every second. Okay. Okay. And that's rate of change. So all we're going to do the rest of the time, we've got about 6 problems. We're just going to kind of practice doing what we just did. So as usual, I'd like you to pause the video and try them yourself and then check back in. And while doing this, I would like you to notice what it says for A, B, C, and D for each one of these. Identify what the unit is for the independent, for the dependent, and the unit for the rate of change, and then go ahead and find the numerical part of the rate of change. All right, here we go. Part A, my independent is my horizontal, that's miles. My dependent is gallons. And so when I compare, my dependent would be gallons per mile. How many gallons I use for every mile is what this would tell me. Okay. Let's see what we can figure out for our numbers. So what I'm going to do is I'm going to look on here for what I can feel very confident is some data points. And so we may end up picking slightly different data points. But so I'm looking at this and I'm seeing this point right here. There's a nice intersection, or it appears to be an intersection there at, let's see, what are the units here? By 50, 100, 152. Yeah, so this looks like the point 150 and 5. And then I'm looking at maybe this data point right here at the beginning, and that looks like we've got the independent variable of 0 and the dependent of 15. And so part D, I'm going to figure out what I've got here. And so the way we can do this is often we take the one furthest to the right. So 5, that's my ending dependent variable is 5. My beginning dependent variable is 15. So if I subtract 5 and 15, I get negative 10. So I had a change of negative 10. And that makes sense because I went from 15 down to 5. I went down 10. And then I ended at 150 miles and I started at 0 miles. And so that gives me 150. If I reduce this, I get negative 1/15 gallons per mile. Interpret that. Every mile, I use 1/15 of a gallon, is what this says. All right. Let's go to part 2. Notice in part 2, my independent dependent, my correlation, right, is positive. It's going up. As my independent gets bigger, my dependent gets bigger. So that's a positive correlation. So part A is hours. Part B is pounds of pollution, it looks like, of carbon. Part C then would be my dependent, which would be pounds, divided by my independent, which is hours. Pounds per hour. So now I just need some data points. I'm looking at this point right here is a pretty good one. Looks like 3 hours and 2 pounds. And this one looks like probably 0, 0. So my vertical change, I went up 2 units and I went over 3 units. So 2 pounds every 3 hours. Or if I want to break this down to what we call the unit rate, which is dividing it out and making it over 1, then 2/3 is going to be, and I'll go ahead and approximate it, is 0.667 pounds for every 1 hour, pounds per hour. Okay. All right, and it went up because the more I used, the more pollution created. All right, let's take a look at part 3, number 3. Looks like we have a relationship that is decreasing, so as a negative correlation. We're going down as time increases. A is seconds. B is in feet. What are we talking about here? This is a skydiver after the parachute opens. So time goes by, my distance gets lower and lower, or my height gets lower and lower and lower. All right, so my units then would be in feet per second. Change in feet over change in seconds. And then let's find out the actual numerical change. We're going to go ahead and probably grab that point, which is 0 and 2,000. And looks like we've got a good solid point right there at 30. And, ooh, I was wrong about my 2,000, wasn't I? Looks like, what are we going at by? 500s? 2,500. And this would be 30 and 2,000. So what did I do vertically? I dropped 500. 500 feet. And how many seconds did that take? 0 to 30 is 30 seconds. So overall rate dropped 500 over 30 seconds. But I should probably reduce this the best I can. Looks like I can cross off 0, make it negative 50 over 3. But if I want to know the unit rate, so how much for every 1 second, it would be the 50 divided by 3. And so I'm going to say my rate of change is approximately, because I'm in up rounding, 16.667 feet every second. So sometimes, yeah, it's great. You lost 50 feet over 3 seconds, but our brains don't often work that way. We really want to know about what happens every second. And so this means we're losing about 16 feet every second. All right, number 4 is a positive correlation. Oop, I need to go back and fix this. That reminded me. That should be a negative. Going down 16 feet. All right, this one's a positive correlation, so I should get a positive answer. Looks like ounces. Part B is going to be dollars. The unit on the rate of change is going to be then dollars per ounce. And then what are we going to do here? Looks like we'll probably start at 0, 0. Looks like I've got a good data point either here or here. Doesn't really matter. So what did I do? I went up 1 ounce. Oh, wait, sorry. $1. Hold on. Did I do this wrong? Yes. Okay, no, let me back up. Dollars per ounce. Okay, no, that's right. So I went up $1 and over 2 ounces. And so that would be 0.5 dollars, so 50 cents per 1 ounce. 50 cents per ounce. $1 for every 2 ounces. Divide that out for the unit rate, 50 cents per ounce. Okay, let's just look at the last two here. All right, so this time I've given it to you in table, so this is still asking the same thing. What's the independent variable? That would be number of people. And part B, that would be in dollars. Part C is going to be dollars per person. So let's come up with a scenario here. What do we got? This is something where we're paying for extra people. With 2 people, $7.90, $3. 3 people it goes up, 4 people it goes up. And so whatever this might be, whether it's, renting a go-kart or going bowling or something, I don't know, but it's something that goes up by the every time we add a person. And so the unit is dollars per person. And so then what is the actual amount? I'm going to do the change, whatever $11.85 is minus $7.90 divided by the change in people. So 3 minus 2. So my cost went from $7.90 to $11.85 when I went up 1 person. So if I subtract that, I'll just go ahead and use a calculator. Minus $7.90 looks like I'm going up $3.95 per person. All right. And then on our last one here, looks like our independent is going to be hours. And our dependent is going to be degrees Fahrenheit. Meaning our C, our unit for our rate of change, is going to be degrees Fahrenheit per hour. So I don't know what this scenario is, but as time goes by, looks like my temperature is either going up or down. In this case, it looks like it's going up. I want you to notice that in this case, we're not going up by a single hour here. Like it just can't scan the data here. So we just got to be very careful we don't make those assumptions. So let's just pick any set of data. It doesn't really matter. Let's just do these two for fun. So 34 was my ending, and I started at 25. And that took 13 minus 10, or, of course, 3 hours. So over that 3-hour period, what happened? I went up, 9 degrees? 25 plus 10 would be 35, so it looks like 9 degrees. So if I divide that out, I get 3 degrees per 1 hour. All right. And that should be the same no matter what 2 data points I pick here. And just to illustrate that, let's try it. Let's use the last one. So the last one minus the first one, which would make it plus 2. I went up 2 degrees to get to 0 and then 34 more degrees to get to 34, which gives us a 36-degree change. And that took 13 minus 1 hours, or 12 hours. And 36 divided by 12 is still 3 degrees per hour. Okay. All right. Well, that is rates of change. We'll continue with this on the next lesson. And let me know if you have any questions.